Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel tanmoyChem. Today's topic of discussion is on MCQ and the question is in front of you. I request you please pause the video, try by yourself, and whatever answer you get please write in the comment box along with few words as explanation. I believe you have tried, so let's start. Now question is whether the below mentioned molecule could be hydrogenated most easily. What do I mean? See, if you look at here in this four option, all contain one benzene ring. Benzene ring means obviously there is carbon-carbon double bond or pi bond. So here I am talking about hydrogenation of these carbon-carbon double bond to their corresponding saturated analog, which could be done most easily. That is the question. So in order to get the answer, let's know a little bit about the hydrogenation of aliphatic and aromatic carbon-carbon double bond. So here if you look at it's an aliphatic carbon-carbon double bond containing molecule, and if you add it hydrogen in presence of catalysts like palladium, platinum, nickel, then this hydrogen will be added these two carbons. Why? Because these two carbon have a pi bond. Pi bond is made by parallel or sidewise overlap, which is not that much stable compared to sigma bond. So you can see here sigma bonds. Sigma bonds are actually stronger because they are constructed by head-on or end-to-end overlap of the atoms. So it's a stable. So that's why reaction happens, and compared to alkene, this alkene is more stable, and this is the driving force. Similarly, if you look at this benzene, it also has a pi bond. If you take catalyst like those nickel, palladium, platinum, hydrogen, little drastic condition needed to produce these cyclohexane C6H12. By the way, these hydrogens are actually came from this. Originally every carbon already has one hydrogen because benzene formula is C6H6. Now, what do I mean by this stability? If I represent this phenomena graphically, you can understand this carbon-carbon. Let's take this example of aliphatic one. So here the energy of aliphatic carbon-carbon double bond. So if you hydrogenate, it will come here. So overall this is an energy of activation. So through this it will come to this product. Agree? So now how much energy is actually released? So this amount of energy is actually released. Now if this is an alkene, obviously not that much stable, but if you take benzene, its stability may be here. I'm just giving a rough idea, I'm not saying exactly. So you can expect that when you do hydrogenation, your product energy may be here. Okay, this is. Now please don't go any confusion about the substitution. I'm not going, I want to give you a feelings. So now here through this energy of activation, this pathway, it will come to the product. Now if I draw, this is actually the NEET stabilization, delta H2. So this is delta H1, and obviously this delta H1 is actually greater than this delta H2, means more amount of energy is released during the hydrogenation of aliphatic carbon-carbon double bond compared to aromatic, and this energy comes out because during this reaction it's called as heat of hydrogenation, and this is actually a deciding factor for determining the stability of alkene. How? So if a alkene, for example this benzene, it is more stable, so heat of hydrogenation is less. So from there, obviously here one important point, end product must be same, then you can compare properly. By the way, I know this information or this explanation may not be adequate for that purpose. I request you please visit a dedicated lecture I have already uploaded. I shall provide the link in the I button and description box for further learning. So from here one part we understand that if a molecule is less stable, so if a less stable means it is more reactive, so it will react faster and it will release more amount of energy. So this more amount of energy release is the driving force for this reaction. And second, if it is actually more stable, then it doesn't have any tendency, because the driving force, I mean energy output, is not that much high. So that means you can expect that, sir, it will not be that much interested to participate in hydrogenation, and that's why for benzene hydrogenation, remember student, drastic conditions are needed compared to the hydrogenation of aliphatic counterpart or aliphatic carbon-carbon double bonds. So now from there we understand that more the stability, less is the reactivity. Now let's look at next question. which of the aromatic compound, I mean this benzene nucleus, have maximum stability? So these question could be answered based on their aromaticity. By the way, means I can say who is actually maximum aromatic, because aromaticity means stability. So according to Huckel rule, if I say cyclic, planar, conjugated and 4n plus 2 number of pi electron, so this thing, and in case of benzene it is satisfied. By the way, if you want to know more on Huckel rule, please visit one dedicated lecture I have already uploaded. Now, so here if you look at the substitution is different. Here 4 methyl and here 1 cyclopentane ring, actually pentene I should say, because these two carbons are sp2 hybridized because attached to this aromatic ring. Here 2 5-member rings are there. So compared to this, option B, C has more ring strength. And in case of option D, you can see 1, 2, 3 rings are fused together. I repeat, these 3 5-member rings are fused together. So there is a severe angle strength. Why? Because here the angle is expected to be 120 degree, but here the actually for 5-member ring the angle is 107 degree. So there is a severe. Now if you look at here, this is an sp3 carbon. So here the angle should be 109 degree 28 minute. Although it is not possible here because of this cyclic arrangement. So you can expect that this molecule have severe angle strain. Severe angle strain, and that is actually a destabilizing factor. So in order to avoid that destabilization, the molecule sacrifices its aromaticity, means the molecule sacrifices its stability, and you can visualize this phenomena better in case of a football. You can, where you can see one hexagon is surrounded by 5 pentagons, and further if you want to know, you can look at fullerenes. They have such kind of structure. So because of this arrangement, these molecule deviates from planarity. So it is actually not planar. Since it is not planar, according to Huckel rule, the third option, conjugation, these double bonds are not in conjugated. So conjugation less, delocalization less, stabilization less. So if I say less stable, then indirectly I am talking that this is more reactive. So this is less stable, this is more reactive. So similarly, if it is more reactive, so you can expect that, sir, the heat of hydrogenation is more. So that is the driving force for this reaction. Now sometimes we say one statement that this molecule is very reactive, that's why it reacts faster. What does it mean by energy point of view? So this molecule is more reactive means its energy, this energy is higher. So when it comes to the product, neat amount of energy release is actually more, and that makes the process more spontaneous. I mean delta G is more negative since the energy release is more. Obviously there is an entropy factor, I am not going. So that is the driving force for very spontaneous or very fast reaction of less stable molecule, and because of this angle strength, this molecule is less stable. So it has the maximum actually reactivity. And obviously which of the aromatic molecule have maximum stability? Obviously option A. Now here, what is the relationship between aromaticity versus tendency of hydrogenation? If the molecule is stable because of aromaticity, it has less tendency for hydrogenation. If it doesn't have significant aromatic stability, so it has a more tendency. So I can say option D has maximum tendency for hydrogenation. So which of the below mentioned molecule could be hydrogenated most easily? Option D, because of lesser aromaticity due to lack of planarity in its arrangement, because of the presence of these 3 fused 5-member ring on this benzene nucleus. So this is the overall discussion. I believe this video may be useful. Thanks for watching. See you in my next video. Bye bye.